Hi, I'm John Cox with Safety Operating Systems. Over the last several years, we've been conducting research on in-flight smoke and fires, and in the recent few years, more specifically on lithium battery fires. So I'd like to talk a little bit today about what are you going to do with a lithium battery fire on your airplane. Let me show you what occurs when an actual lithium battery fire happens. Listen to the panic that it incurs. So there's a lot of issues in addition to the fire itself and the smoke that we as flight crew members have to deal with. This occurred in 2005 in Los Angeles International Airport. You can see the smoke rising from the device, from the computer. You hear people reacting. Once this process starts, until the device is cooled, it's going to continue. Even when you put, for example, dry chemical extinguishing agent on it, this thermal runaway continues, and you can see the smoke continuing to rise as the thermal runaway continues, even after the discharge of dry chemical extinguishers. This is also true of halon. Both will extinguish the open flame, but they do not stop or deal with the thermal runaway itself. FAA, in collecting statistics through the Security and Hazardous Materials Safety Office, has noted 129 events of lithium batteries carried as cargo or baggage since 1991. But more significant to that is 22 of those events, or 17%, occurred in 2016 alone. So we're seeing an increase in the number of events, and the trend continues to rise. It's one of the very few threats in aviation that it's actually rising. To give you a couple of examples, in July of 2016, a passenger cell phone battery exploded in flight. It was extinguished by the crew, but they chose to use halon extinguishers. Of a greater significance was an event that occurred in August of 2016, where a smartphone went into thermal runaway. The flight attendants tried to deal with it. They got it extinguished, but in doing so, they had injuries to both of their hands. This is a major concern because the incapacitation of flight crew members is a very serious concern, particularly in the case of business aircraft where there may not be flight attendants, and we'll be talking about the incapacitation of one of the pilots. This is what can occur when an iPad is crushed by a seat and goes into thermal runaway. The airlines are seeing this reasonably regularly, and crushing or dropping devices is one of the leading causes of thermal runaways. This is an iPhone 6 that occurred in March 19th of this year. It too went into thermal runaway. On September the 7th, this is a Galaxy phone or Samsung phone. It went into thermal runaway. And this is one of the earlier Galaxy Note 2s that went into thermal runaway in September the 23rd of 2016. No device with a lithium battery in it is immune from this problem. This is a Surface tablet that went into thermal runaway. And the well-known Samsung Galaxy Note problems, this is the replacement unit. It too had problems and has also now been recalled. This was on an airplane, and it created quite a large amount of smoke, causing the airplane to be evacuated. So how hot does it get? Something over 1,000 degrees. In the neighborhood, FAA says somewhere between 1,000 and 1,100 degrees Fahrenheit. That is one of the many issues that a flight crew member has to deal with, is that the discharge coming out during a thermal discharge, if it touches your skin, that gel can be upwards of 1,000 degrees, causing significant third-degree burns. They're also unpredictable. We have no means to determine whether a device, a cell, when it goes into thermal runaway, will spew a little bit of smoke, will explode, or something in between. So a flight crew member facing an overheating device must consider the fact that it can explode at any time. Let me show you an FAA test of a Surface tablet battery that was put into thermal runaway in Atlantic City. You can see the discharging of the thermal, of the individual cells. And as they discharge, the fire grows because all the elements are here: fuel, oxygen, and ignition. You see large amounts of smoke. This smoke is toxic. It's a mucous membrane irritant, and it can be explosive. We'll talk a little bit more about the flammability of the smoke later in the presentation. But these can cause significant damage to your airplane. FAA testing has been going on for a number of years. They've done full-scale battery tests with a mixture of lithium ion and lithium metal, and they've presented this industry-wide, the most recent being in 2013. In that report, they note that the capability of thermal runaway through a cell defect, damage, heat, rapid discharge, overcharging, thermal runaway results in high case temperatures exceeding 1100 degrees Fahrenheit. Release of flammable electrolyte, the gel, can generate sufficient heat to cause adjacent cells to go into thermal runaway. Once this process starts, from cell to cell to cell, the heat transfers and this thermal runaway process continues until all the cells are exhausted. It's important to note that the airflow pattern in the airplane can have a significant effect on the behavior of the battery fire, and of even more importance, the smoke penetration. Smoke is a very significant part of this overall threat. Smoke in the airplane is something that needs to be dealt with. It needs to be dealt with effectively. In the case of business aircraft, the consideration for passenger smoke hoods should be considered, because if you do not contain the device, you may have passengers that are subjected to this mucous membrane, very high irritant smoke. So if we don't contain it, smoke hoods may be a possibility. Smoke can be a major concern. Let me give you an example. In this video, which is a customs facility in Colombia, the customs officer on the upper left is a very conscientious customs officer, and as we all know, they have an issue in Colombia and that part of South America with contraband. So this is a conscientious agent. He's checking the bag carefully. He also wants to look at the box that's adjacent to it. So he opens the box, and within the box, we think it's a flashlight. But he looks in that and concludes that it would be a good idea to have a look to see if there's anything within the flashlight. So he forces it open, and in so doing, shorts it. Once shorted, it goes into an instantaneous thermal runaway, and you can see the growing amount of smoke in the room. Now, the FAA in Atlantic City testing has said that they noticed a 50% obscuration within 5 minutes. This video, from the time that he shorts it until you can no longer see the table is about 35 seconds. My question is, what are you going to do with this much smoke in your airplane? What are you going to do? Tests have shown that with even a very high ventilation rate, as high as 1 full cabin exchange per minute, which is well in excess of most aircraft, a typical lithium battery could pose significant hazard within the flight deck environment and could present a catastrophic risk. This too is out of the FAA report. So let me show you on the flight deck what a smoke event can look like. At the test facility, the tech center in Atlantic City, they have a 727 that they use for smoke testing. This is inside the flight deck of the 727. Within the cage is a laptop battery that they are forcing into thermal runaway. There are 3 nozzles above it. They have halon, and each time an open fire breaks out, they immediately discharge halon on it to extinguish the open fire. This was virtually an instantaneous response, but the point is how much smoke is going to be generated in a large flight deck, and how quickly. As cell after cell ignites, the quantity of the smoke goes up rapidly. The pilots in a condition like this would have their smoke goggles and mask on, but how are they going to see to fly the airplane? Because the vision obscuration grows worse by the minute, and this is from a single laptop. The FAA said 50% obscuration within 5 minutes in some of their tests. This is virtually 100% obscuration in less than a minute. So even with the goggles and mask in place, how are you going to fly the airplane? That's what it looks like with just an oxygen mask and goggles in place. What are you going to see? Are you going to be able to see the attitude indicator or PFD? Let's take a look at a very compelling example of what a flight deck full of smoke looks like. This is the cockpit voice recorder transcript from a UPS 747 that took off out of Dubai. And at 17 minutes after 3 p.m., the captain informed air traffic control that the cockpit was full of smoke. He said, "We're full, the cockpit's full of smoke. We're attempting to turn to a 130. Please have the equipment standing by in Dubai." Less than a minute later, between the 2 pilots, this conversation, "Can you see anything?" The first officer, "No, I can't see anything." So from the very outset of this emergency, visibility was a major problem. The first officer mentions on several occasions the difficulty in getting critical data for the instrument landing system tuned properly because he couldn't see. Try to get Dubai in the flight management computer. First officer responds, "I can't see the flight management computer." 2 minutes. UPS 6, expect 12 left the runway and proceed direct to the final at your discretion. "All right, we're doing our best. Give me a heading if you can. I can't see." This is 2 minutes after the initial report. "I've got no oxygen. I can't breathe," the captain says after 3 minutes after the initial report. "Get me oxygen. I don't know where to get it. You fly." The captain, "I can't see." At this point, the captain gets out of his seat, goes to try to locate the supplemental oxygen in the jump seat area behind the flight deck. He never returns. He's overcome by the smoke. The first officer's left to fly the airplane by himself. They were unable to change frequencies and had to use a relay airplane, and they informed them they would stay on the Bahrain frequency because they could not see to change the frequency. Sir, we're going to have to stay with you. We cannot see the radios. The radios on there are about an arm's length from the first officer. I'd like to immediately get vectors to the nearest airport. The first officer says 8 minutes after the initial report, I'm going to need radar guidance, I can't see. Shortly thereafter, he says, we're flying blind. I have no visual indicators to say 10,000 feet. I can't see out the window. We're going to have to work together on this. I'd like to get a descent to 9,000. He can't see outside and he can't see his flight instruments. In the final report, GCAA recommended that the visibility should be sufficient to view the attitude indicator or primary flight display and to see outside the airplane for landing. In addition, it's imperative that the crew be able to view the instruments and navigate. They must be able to see to program the flight management computer and audio control panels. This is a critical element of our mitigations to a lithium battery fire, because this is all they had. And you cannot see. The transcript proves as hard as they fought, they were unable to see. So what has the industry done? Well, UPS installed EVAS throughout their entire fleet as the means of mitigation to the visibility issue. Other airlines have installed it. FAA installed it on their entire fleet, and other VIP and VVIP operators have installed it. This is a means of vision assurance technology that is being applied today. We've seen continuous smoke accidents such as Federal Express 1406, Swiss Air 111 off of Peggy's Cove in Canada, AirTran 913 in Greensboro, UPS 6 in Dubai, and Asiana 991 in South Korea, UPS 1307 in Philadelphia. Each of these accidents were continuous smoke accidents. A number of them were lithium battery accidents. But when we certify our airplanes today, we don't certify them for continuous smoke, because the advisory circular that deals with smoke is the advisory circular 25.9A, and it says, although the FAA does not require consideration of continuous smoke, the FAA recommends it. And to this point, to this day, only one airplane has followed the FAA recommendations, and that's the Gulfstream 650. They meet the FAA recommendations by using EVAS. They can deal with continuous smoke in their airplane. No other manufacturer has met this recommendation. Since 2005, the Royal Aeronautical Society has published a specialist document, Smoke and Fire in Transport Aircraft. It's been updated in 2013, 2014, and 2015. The Royal Aeronautical Society recommended revising the advisory circular 25.9A so that smoke evacuation tests are conducted with continuous generated smoke. Vision assurance technology to improve pilot visibility during times of continuous smoke on the flight deck. The visibility in the flight deck should be good enough so to see the attitude indicator or primary flight display and to see outside the airplane for landing. These recommendations were made before 2010, but by 2014, during the update, the Society recognized that one of the largest trends is the growth of in-flight fires due to the transportation of lithium batteries. Gray market batteries and their chargers are a risk. In addition, gray market chargers being utilized on OEM batteries can also be a risk. Thermal containment technology is available and should be considered for carriage in the cabin by all operators. This is the current recommendation by the Royal Aeronautical Society. So the current FAA guidance on how to deal with this is do not use fire-resistant burn bags to isolate lithium battery type fires. Transferring a burning device into a burn bag may be extremely hazardous. Do not move the device until you're certain the fire is extinguished and the device is cool. This is from the FAA SAFO 09013 supplement and is a direct quote. In 2016, in January, FAA testing has shown that a single cell, whether metal or ion, in a thermal runaway will spread to adjacent cells. The heat will transfer, causing sequential thermal runaways and explosions to spread to the neighboring cells. And it doesn't matter what initiates it. It can be a short within the battery that can be caused by manufacturing. It can be damage. It can be heat produced by the environment. It doesn't matter what starts it. What does matter is the fact that once this starts, you have to cool it. And there's a lot of them out there. In 2016, it's expected that the industry will produce about 6 billion lithium battery cells, and that number will grow over time. The demand by our society for lithium batteries continues to rise. They are in virtually every electronic device now. They are a part of modern life, so we as an industry have no choice but to mitigate it because we're not going to eliminate this threat. There are two different basic types. There's lithium metal, there's lithium ion, and lithium polymer. One is rechargeable, one is not, but from a firefighting standpoint, we have to treat them the same. Lithium metal is very hard to extinguish and burns at an actually hotter rate, but it burns through its fuel more quickly. Lithium ion water is effective in cooling the device, and consequently, we need to have improved training for our flight attendants and pilots that may be facing this kind of risk. And there are questions that remain. If we can protect the firefighter, the crew member that's responsible for fighting this fire, if they're adequately protected, does the FAA guidance of don't move the device appropriate? And if the threat can be contained, is the FAA guidance appropriate? If it can be contained, will it stop the panic? So we need to look very carefully at containment. And the recommendation not to move an overheating device, is it always the best choice? What about on the flight deck? What about a device that is on or near the in-flight entertainment system or other critical electronics? Are we going to want to pour water or a non-alcoholic liquid in to that environment? We're working on better guidance. We're working on better language. We're working with the FAA. Flight Safety Foundation, the Royal Aeronautical Society, and the Honorable Company of Air Pilots has proposed language to give the flight crew members better information to use their professional judgment into whether to move the device or not, and to better assess what they can do. So far, the FAA has taken the input but has not acted. We need to improve the guidance to our flight crew members. We need to improve the training to our flight crew members. We need to install vision assurance technology on the remainder of the fleet. We need to install containment technology that fully contains the overheating device and the vapor. Those 4 steps can go a long way in answering the question, what are you going to do about a lithium battery fire? Over the last 4 years, as I've done presentations on lithium battery fires around the world, one of the recurring questions I get is, okay, you've described the problem. We recognize that there need for mitigation. What do we do? So let me specifically try to answer those questions. First, we need to apply pressure to the regulators for better guidance. The Royal Aeronautical Society, Honorable Company of Air Pilots, and Flight Safety Foundations have agreed on a proposed language that will better help flight crew members should they be faced with a lithium battery fire. those need to be adopted and distributed. Second is training. Operators need better training. They need lithium battery fire specific training. This can be done at a minimal cost, but it is a skill set that flight crew members need. Third, vision assurance technology. Gulfstream in their 650 has adopted the EVAS system, which is a very effective means of maintaining visibility during a continuous smoke event. Operators around the world have adopted it, and the use of this technology utilizing EVAS has proven effective.
The Emergency Vision Assurance System, or EVAS, is an independent system that provides the pilots the ability to see basic instrumentation and out the forward window in an event where dense blinding smoke hinders the crew member's capacity to fly the aircraft. History has shown once the cockpit fills with smoke, the pilots become unable to see their instruments and out the window, even with smoke goggles. EVAS works by displacing the cockpit smoke via an inflatable vision unit that is specifically fitted to the aircraft type. The first thing we do is arm the EVAS. The EVAS restraining strap is loosened, then remove and clear the power unit lid. The lid restraining wire can get wrapped up in the supply hose if not cleared. As the lanyard is pulled from the slot, a circuit is closed, turning on the light and blower. The pilot should ensure the flex hose is completely extended and place the IVU on the glare shield in a single motion to avoid misalignment. The pilot should align the Velcro on the glare shield to the IVU wrapper. If the blower does not start automatically, it should be manually started by depressing the master start switch. The master switch allows the pilot to turn on and off the blower. Strategically shutting off the blower will extend battery life. Now we will deploy the EVAS. Inflation is accomplished by holding the IVU on the glare shield and sharply pulling on the wrapper tab. While holding the IVU in position, tuck the wrapper ends under the IVU. Gently rake towards you the nearest portion of the IVU. If the unit's tunnel section drops in front of the yoke, place it forward of the yoke. Use both hands to unfold and smooth out the windscreen portion. Place the ends of the IVU to the uppermost corner of the glare shield. Hold in place until the air pressure is adequate to hold the IVU still. Assist the inflation process as needed by smoothing the IVU out. The unit will inflate in about 30 seconds. EVAS does not provide a complete view of all the instrumentation in the cockpit. The basic navigation instruments and the forward window are all that are covered. Either unit is capable of repositioning the IVU to view other portions of the cockpit, but policy dictates only the pilot monitoring should do so. The IVU has 3 pockets, 2 on the side and 1 on the bottom, allowing both pilots to view checklist, approach charts, and other documents as needed.
Containment technology. This technology has to be also incorporated because containing the device is very critical. The only device that fully contains all the vapor as well as the device itself while providing adequate protection for a flight crew member is plane guard.
At the first sign of a problem, the plane guard case is brought to the scene of the smoking or burning personal electronic device, also known as a PED. Plane guard is then placed in the aisle, preferably 1 row of seats in front of the malfunctioning PED so that the adjoining seat backs can shield the flight attendant while preparation for using the plane guard is made. Open both latches on the plane guard case. Next, open the case lid and remove the scoop while leaving the plane guard case in the open position. While holding the scoop by the horizontal handle, pull on the red pull tag to fully extend the slide. This will allow the safety glasses and leather gloves to fall onto the seat or other suitable surface. Then lay the open scoop on the open plane guard case or other suitable surface. Put on the safety glasses and leather gloves. Then, with one hand, pick up the open scoop by the handle on the large flat side. Next, using the open scoop as a shield, approach the burning PED. Now cover the burning PED with the open scoop and push the bottom slide tray under the burning PED until fully closed, safely capturing the device. In the event of a full-blown laptop fire, the scoop can be used to close the laptop screen as shown. Now pick the scoop up by the handle on the narrow side and drop the scoop back into position in the plain guard case. Quickly close the lid, then close the latches. The PED fire is now safely contained, but there is one more important step. Using a gloved hand, push open the water toggle valve and add at least 4 liters of liquid to the case. Any water-based products will do, such as bottled water, soft drinks, or juice. However, liquids containing alcohol should never be used. Now plain guard with the contained PED is safe to remove from the area. Please note, while full of water, keep plain guard in its normal upright position with the handle on top.
Utilizing these mitigations, we can reduce the risk and the effect of a lithium battery fire to an acceptable level. If we don't, then we're going to see the number of these events continue to rise and the serious nature continue to grow. It's up to us, the industry, to do the necessary steps so that you can answer the question effectively. What are you going to do with a lithium battery fire? If you'd like further information, have questions, or would like to talk about training, we can help you get the necessary information, get the necessary training, and help you adequately mitigate the risk of a lithium battery fire. Thank you.